And core is hopefully the next generation CMB space mission, and has been presented as a proposal by a large collaboration. There are just institutes there, but the names are many more. And what is core? Is a space mission to measure polarization of the millimeter sub-millimeter sky with high purity in polarization, 0.1% of the polarized signal, wide spectral coverage, 15 bands from 45 to about 800 gigahertz, high angular resolution from 23 to 1.3 arc minutes, full width half maximum, and sensitivity of the order of 5 microkelvin arc minute in each CMB band. The science targets of the mission are, of course, the B modes, but also neutrino masses, non-Gaussianity, and new windows on the physics of the interstellar medium, which are gained with the high-resolution observation of polarization. Proposal was submitted to ESA Cosmic Vision, and the white paper can be found there. There is a web page, so you can go and see all the details. In this presentation, I'll focus on technical aspects mostly, because we do want to demonstrate the feasibility of this mission anyway. So the target of B modes of 10 to the minus 3 is incredibly difficult, and to go there we need polarimetric purity, and this is achieved in this design using the polarization modulator as the first element in the optical path of the instrument, and also using single mode very precise Gaussian beams. The sensitivity is improved with respect to Planck, for example, using a very large array. We heard Jean-Michel about the difficulties of the cosmic rays, for example, which were close to limit the performance of Planck. And of course, if you want to go deeper, you need to improve, and there is no way to improve if the limiting factor are cosmic rays other than increasing the number of detectors and increasing the observation time. The other big problem is polarized foregrounds, and we all understood this with WMAP first and with Planck as well. So to go after B modes, we need to clean from polarized foreground, and the only way we have to do that is to have a very wide frequency coverage and have many bands, as many as the parameters describing your foregrounds. This is also useful for the interstellar medium studies, and this has to be coupled with high angular resolution. When I say high, I say at least as Planck. So this is the design of the cartoon we arrived to. And stated very simply, this is as Planck with the polarization modulator in front and with many, many more detectors. But this is a too simplistic description of the instrument. The instrument, as you see, has a polarization modulator, which is this giant reflecting halfway plate, which rotates. And this is the first element encountered by photons reaching the system. Then we have a compact range telescope and a large focal plane. Everything is cold here, and the system is separated by the warm environment through a set of V-grooves, another of the great lessons we had with the Planck system. So let's speak first about the reflecting halfway plate. one of the problems with polarization measurements is that you want to measure polarization in many bands, spanning a wide range of frequencies, but you cannot use one halfway plate for each band. So this is the trick, to use the same halfway plate for many bands, and you have a freestanding wire grid and a mirror, and the distance between the two is tuned so that you can observe all these frequencies. For all these frequencies, the shift in between the ray which is reflected by the polarizer and the ray which is reflected by the mirror is exactly 180 degrees, so you have a halfway plate. Of course, you cannot choose your frequencies as you like. You have a comb of frequencies you can use, but this is okay. This is fine to cover a wide frequency range. The other problem is that the bandwidth of each of the bands is limited. So at high orders, with this n large, you will have very narrow bands. But this is interesting. So this is the comb of halfway plate efficiency, and this is the set of frequencies and bandwidths we implemented in the proposal. As you can see, the high frequency channels have been widened by using matched filters to include several orders of the halfway plate in the same bolometer channel. Is it feasible? Well, there are prototypes, not 1.5 meters wide, but we have 20 centimeters wide prototypes which work quite well. And in this respect, ESA has worked quite well because one technology activity call has been issued to help us in studying this problem. The halfway plate has to be rotated. As you have seen, all this is at cryogenic temperature, so we need the cryogenic rotator. We have prototypes of rotators which are quite reliable. In the core proposal, we opted for a room temperature motor and a log shaft to move the wave plate using a room temperature motor. Now, let's see. From the science, I'll skip most of this, but I just want to say that with the 5 microkelvin arc-minute sensitivity, we have enough sensitivity to achieve B modes at the 10 to the minus 3 R level, and to measure the sum of neutrino masses down to the 50 millielectron volt level, which is good enough to establish the hierarchy of the neutrino masses. Also, the frequency coverage is essential, as I said, to foreground, to subtract the foregrounds, but also to cover the wide range of emission of interstellar dust, and to study the galactic magnetic field through the polarization of interstellar dust emission. Now, to do this, we need the sensitivity. And for 5 microkelvin arc-minute, we need a lot of detectors. As you, this figure has been shown by Jean-Michel before, and it's impressive. It's even too impressive because, of course, these single samples stick out, but there are many, many more good samples in the without cosmic ray hits. But anyway, hits are there, and so it's hopeless to increase the raw sensitivity of the detectors. You have to increase the number of detectors to do this job, and so this is our real estate for the focal plane. And you see the number of detectors for each band is quite impressive, for a total of 4,200 detectors. resulting in a total focal plane sensitivity of about 1.5 microkelvin per minute in 4 years of operation of the instrument. Of course, everybody knows that this is raw sensitivity, and there will be systematic effects, there will be foregrounds, but the idea is that even if you use most of the other channels for foreground cleaning, then the clean channels still have a raw sensitivity of 5 microkelvin per minute, which is our goal. And if you compare to what we are achieving with the Planck, core is getting here. So you see the improvement, okay? We did a very good exercise to show that imperfect foreground modeling gives residuals which are low enough to allow, again, the detection of R equal 10 to the minus 3, and also to use delensing at the level of basically the final noise. This is the giant focal plane. It's 40 centimeters in diameter, and if you want to feed it, you better have a very good telescope with a very good performance in a wide focal plane. As you see, of course, high frequency channels are in the center, low frequency channels are on the edge. All are diffraction limited single mode pixels to have high circular Gaussian beams. The bolometers are the immediate option for this mission because, as you heard even in this conference, they are being used already in large arrays at Sao Paulo, at Atacama. The multiplexing readout has been developed and they work very well. There are other emerging options which could improve in raw sensitivity against bolometers, in the sense that, for example, the solution with the cold electron bolometers has a sensitive area which is incredibly small, so the sensitivity to cosmic rays is reduced by several orders of magnitude due to the very small area. And this area is effectively thermally insulated from the rest of the detector. So even if there are hits in the rest of the detector, they don't propagate on the sensor. So this is a very promising technology. Has not been selected as the baseline for this mission because it's a bit too early, but I'm expecting a very quick development of this technology. And also the other technology is kinetic inductance detectors, which are now being developed on membranes to reduce their sensitivity to cosmic rays. I said about the telescope, our friends in Maynooth have solved a lot of the problems for this kind of large focal plane. The ellipticity of the beams is of the order of 5% at the edges. So you may say, well, 5% is a bit too much. Yes. And here again, ESA came to the rescue because they issued another technology development occasion for studying compact focal planes. So there are only two ways to compactify this focal plane. One is to have several bands in the same pixel, like with the multichroic approach, which has been developed in Berkeley, has been proposed for Lightbird. We heard about this. The other is to have both polarization in each pixel. And this can shrink the size of the focal plane by a good factor. There are technical activity to make good orthomode transducers. For the low frequency channels, the technology is very advanced. For the higher frequency channels, there are good results. And so this is what people is doing with this, is hoping to do with this new technology development effort. The mission. We need the full sky coverage. We need no atmosphere, of course, going up to the terahertz range. We need the thermal stability. We need low signals from the side lobes. And again, I mean, we need an L2 mission. The mass of this system is about 1.8 tons. The orbit is a halo orbit in L2, similar to the Herschel one. The launcher can be Soyuz. The raw data rate is 18 megabits per second, which can be compressed to 4.5 if we use the same algorithm as Planck. As designed, the spin axis of the mission is the Sun-Earth direction, so we have this antenna, which is a high-gain antenna, which is directly pointed towards the Earth, and this makes possible to download the 4.5 megabits per second in 2 hours every day. So this is the system we have proposed. It was not selected for M3 in 2010, but the importance was recognized, and as I said, the technology development program has been supported. Meanwhile, we had several progresses. First of all, the results of Planck, which give a good boost to this kind of activities. Telescope detectors, cooling chains are completely validated by Planck at this point. And the control of systematic effects, which again, most of the systematic effects are mitigated by the presence of the rotating half-wave plate, have also been demonstrated, this control, with ground-based and balloon-borne experiment. The next opportunity we have for this mission is M4 in 2014, so we will reapply, we will update the proposal with the results of the activities we have carried out in this. Meanwhile, ESA has produced the call for white paper for the definition of L2 and L3 missions. And is a call for science teams and questions for the L-class missions, which are currently planned for these years, so I'll be retired, but anyway, we have a dream as a community. This call offers the opportunity to define this dream in view of a very ambitious mission. You will say, core is already ambition. Yes, but we can do more than that. And that would not fit the M size, that would maybe fit the L size. And we had a number of informal meetings and discussions, so we do plan to submit a white paper stressing which science themes. Well, what the dream is, again, from the practical point of view, is to have a high resolution millimeter to far infrared polarization measurement and high accuracy absolute spectral measurements. So you see, it's the combination of two instruments. One is a polarimeter better than core. The other is a absolute spectrometer. I think this is a killer combination because you see the number of deep questions which can be answered by this mission. Having the combination of a high-resolution polarimeter and an absolute spectrometer, maybe the absolute spectrometer will not have a high angular resolution, but can be used to calibrate the high-resolution polarimeter. And conversely, the spectrometer, the results of the spectrometers, the data of the spectrometers can be cleaned by the measurement of the polarimeter with the high angular resolution. So I think this is a way in which two instruments complement each other quite well. We have a Stroman sample Stroman mission. It is required in the call. It's not just science. You have to design a sketch of the mission, and this will be based on the heritage, of course, from Planck from the core proposal, and for the spectrometers there have been several activities going on. So we have material to produce a realistic Stroman mission. Jacques de la Bruyne already has good ideas, and I'm just showing his ideas. Here you have a spectrometer aligned to the spin axis of the instrument, while the polarimeter with the large telescope is offset by some 40-45 degrees. And while the spin axis precedes, and in one day it does a full circle, the other instrument, the polarimeter, spins around the main axis in 10 or 20 seconds. So this is a very fast scan of the sky, which allows you to measure polarization without probably the need of a halfway plate, but this has to be demonstrated. Anyway, the other idea is that this can be a dual satellite mission. It's a large mission. And the first one would have the observatory, let's say this one. The other one would be a relay satellite for communication with a high gain antenna pointed towards the Earth, which would not be possible with this scan strategy, of course, on the main satellite, and with a calibrator, a set of calibrator sources to calibrate the beam and the sensitivity, the responsivity of the instrument. Okay, maybe this is just a dream, but we want to try it, and of course, collaboration will be very welcome, because the white paper is due on May 24th this year, which is very close. So an invitation email will be circulated soon if anybody wants to help in this activity. Thank you.
Thank you, Paolo. We just have time just for one question, because it's getting close to... Well,
killer question.
Any? Okay.
Just very quickly, can you summarize the difference between core and PIXI?
Oh, well, core is a polarimeter, PIXI is an absolute spectrometer, so they are completely different in the implementation and in the targets, in the sense that the spectrometer is mainly to see monopole spectrum. There is the possibility to measure polarization with a Fourier transform spectrometer like PIXI. I have to say this has not been demonstrated very deeply, so it's a possibility, but subject to several problems, which technical problems. But anyway, yes, you can do polarization. The systematic effects are not clear to me. Anyway, the angular scales PIXI is sensitive to are quite broad, while with core we wanted to explore all the spectrum of the polarization.
Okay, thank you very much. So can we thank Paolo and all our speakers this morning. Just a few announcements. First of all, that the restaurant closes at 2, so if you want lunch, you need to get lunch before 2. We reconvene at 2:10. And also, the speakers and panelists for this afternoon, if they haven't submitted their talk,